Okay, this is the 5th video in Chapter 8. We're going to be looking at the last category of types of chemical reactions, double replacement reactions. And double replacement reactions are reactions where you have two ionic compounds that are dissolved in water. So usually ionic compounds don't react unless they're molten or in their liquid state so that the particles are mobilized. So the two ways that happens is either with heat, but that would be, most compounds decompose before they melt at that stage. But most of the time they're dissolved in water. So compounds A, B, and C, D here are ionic compounds that are aqueous or dissolved in water. Okay, and so we have two ionic compounds. Now let's remember what an ionic compound is. If I write that AB is an example of an ionic compound, then basically what I mean is that A is the cation and B is the anion. And cations, remember, have positive charges, so I'm going to put plus X there. Anions have negative charges. I don't know why I just put a plus there. I think I was talking. Anions have negative charges. So here we have an aqueous solution. Now what does that mean? You got a beaker of water. You throw a solid ionic compound in it. When you throw the solid ionic compound in, if it's aqueous, it means it's soluble in that water. What that does is dissociates or breaks the ions apart. They become free from one another. They're not held together by those Coulombic forces anymore. They interact with the water molecules, which are polar. So what that really means is that we've got A cations, I'm just going to say plus for generic purposes, floating around, and we've got B anions floating around. They're dissociated or separate from one another. All right. If we react that with CD, CD is another example of an aqueous compound. Okay. It's an ionic compound that's been dissolved in water, so the ions dissociate or break apart from one another. They become free. So C would be the cation, once again, dissociated from D, which is the anion. Okay, so they're all just floating around in solution. Now C and D and A and B are soluble in water. They're aqueous. That means they would prefer to be hanging out in the water, separated from one another, versus being combined together. Okay, we need to realize that. Now what we're physically doing, I know I'm writing over the notes, but I'll clear the screen. We'll write over them again. But I want you to understand what's happening. If I say, hey, take these reactants, aqueous AB plus aqueous CD, and I want you to see if a chemical reaction will occur. I'm asking you to take this solution and this solution and pour them together. So maybe you've got this big empty beaker here. And I'm saying, hey, pour these solutions together and see if a chemical reaction occurs. Okay? A chemical reaction is when bonds are broken or formed. Now all the bonds are broken here. See that C and D, they're dissociated from one another. They're aqueous, hanging out in solution. If I react this together, or combine these two, not react them, if a reaction takes place, some of the ions will combine to make molecules. Okay? So if I've got A, B, and C, D here, B is an anion, C is a cation, D is an anion. We already know that A and B would rather hang out in solution than to recombine, because that's what they did here. They prefer to be aqueous or separated, dissolved apart. C and D are the same way. But when I combine these two together, we have a new environment. We have a new mixture, because now we've got A, B, C, and D all in the same reaction flask or container. If they're colliding along, because remember, they're in their pseudo-liquid state, they're in solution, so these ions, are moving around. They're translating through space, slipping and sliding with the water molecules and against one another. We know the cations are going to repel each other, because like charges repel, so A and C are not going to combine. But what happens if A comes up to D, and it says, I'm a cation, there's D, the anion. We know cations and anions are attracted. If they come together in space while jostling around in the solution, if A and D decide that they would like to be together more than in the solution, or they would form a tighter bond than interacting with the water in the solution, they could actually combine to form a compound. And if they form a compound, there's a chemical bond ionically produced, or covalently, depends on what we're looking at here. And they will no longer be part of the solution. They will be part of themselves. So they will come out of the solution, and I don't want to say they'll precipitate yet, because that's one of the things that could happen. But they will come out of the solution somehow and no longer be a part of it. Instead of mixing and mingling, kind of like the single scene, and it's like, oh, we're a couple, we're not on the market anymore. We're going to just combine with each other and not interact with anyone else. Then a chemical reaction will occur, and this is my way of writing a chemical reaction. A chemical reaction will take place. Now, what happens if A and D came across each other, the new cation and anions, or it could be B and C, but neither one of them liked to interact with one another, and they just still said, you're pretty nice, but just like with B, I'd rather hang out in solution. There wasn't a heavy interaction to form a chemical bond there. Well, then no reaction would take place. You would just have a mixture of A, B, C, and D cations and anions. But in order for a reaction to take place, there has to be evidence of a reaction. So what's going to happen is for single and double displacement reactions, I'll start here now, we have two ionic solutions coming together, and those ionic solutions are going to be mixed to see if a chemical reaction occurs. A chemical reaction will not always occur, but if one occurs, the cations will exchange anions. So A, which is a cation, will switch places with C, a double displacement, and you'll form the new ionic compounds after the switch. How do we know whether or not a reaction takes place? We're going to look for evidence of a chemical change. And this is really, you can do this in lab literally with your five senses. Seeing, touching, on the outside of a beaker, not chemicals, but you can use your senses to detect. You can listen. Do I hear hissing of a gas being formed? So you can hear whether or not, or see, or feel whether or not a chemical change takes place. This will be, I'll show you a way to do this on paper though. What if you're not in lab and I ask you, hey, if I had these chemicals, not do you have them, could those produce a chemical reaction? There's certain evidence that you could predict whether or not the reaction would occur or not. What's the first one? Obviously it's here. The first one is evolution of heat. This is the one piece where, as you go further in chemistry and you become more experienced, you'd probably be able to predict the reaction. You're just going to be accustomed to the reactions. Usually acid and some bases, strong acid and base will produce heat. If you have a strong acid or a base, they'll usually react with another acid or base and they'll produce heat. At this stage in the game, I wouldn't expect you to be able to predict whether or not heat would evolve in a reaction or be formed. So that would be information I would give you. If I said, hey, I reacted this ionic compound solution and this ionic solution, and hey, the reaction got hot, that's evidence that the mixture got hot. That's evidence that a reaction would possibly occur. So I'd give you that information. What else could you look for evidence that a chemical reaction took place? You should know these. So know these three. The second would be formation of a precipitate. What a precipitate is you've got these three phases of matter. You've got solid, liquid, and gas. Now, when we're in a solution form, solutions are pseudo-liquids. They're not pure substances. Usually liquids are for pure substances. But a solution would also be an example of a liquid type state, a mobile particle state. Whenever something precipitates, it goes from a higher energy particle state, mobility-wise, to a lower energy particle state. Remember, liquids can move, and the particles of solids typically do not move around in space. They might wiggle and jiggle, but they're not moving around. A precipitate is any time you go down from a higher energy particle to a lower energy, kinetic energy particle. So in the case of double displacements, since everything is aqueous or in solution, a precipitate would form whenever a solid, or we'd say a precipitate form whenever a solid is produced. And solids would be things that are insoluble, ionic compounds that are insoluble in water. Okay? So how would you predict whether or not a precipitate or a solid would drop out of solution? Well, you're going to have to use something called the solubility chart. oops, let me write that down here. A solubility chart. And this would be something that I would give you on an exam too. So you have the activity series for single displacement reactions. For double displacement reactions, one of the ways you could predict whether or not a chemical change took place is if a precipitate formed. If something was insoluble in water, in that aqueous solution. So how do you know if precipitate formed? You're going to use a solubility chart. Okay, so where do you find a solubility chart? Well, there's one online. Actually, in the completed notes, you can, if you print those out, or just the last page, page 6, you'll find a solubility table there. Also, in your book, because I'll give you one, so you might not want to print one out. But in your book, there are solubility rules in the chapter, but if you go to the appendix, which is the back of the book, in Appendix 17, so A17, there will be a page like this. And at the top it will say, solubility table. So Appendix A17 in your book. I promise you'll be able to find it. If you look in the back of the book, you'll find the solubility table. And solubility tables are generally in different books or in different forms. Here's an example of one. And basically what it is a solubility table is an ionic compound soluble in water. So we're testing all of these as soluble in water. And there's going to be 3 different outcomes. If something's soluble in water, you're going to see an AQ written beside it. Soluble. That means soluble in water. Soluble in water. The second symbol you're going to see in here is an I. An I means insoluble in water, or it does not dissolve in water. An I will tell you that a precipitate forms. If you see an I anywhere on this table, it means that if those 2 substances were formed, they would not be soluble in water, they would precipitate out, or a solid would drop out of the solution. Alright, and then the third thing you're going to see is an SLAQ, like right here. That means slightly aqueous. It's semi-soluble in water, but not completely. So those are the 3 things you're going to see on the chart. Now, ionic compounds are always cations and anions. So the chart is usually bigger than this. But it contains several different types of cations. So over here you've got your cations on the left here. And on the top we have our anions. So you can look at this as a kind of a grid, like an XY coordinate type thing. If I had, let's say, ammonium hydroxide. Ammonium is NH4+, hydroxide is OH-. If I predicted, I could produce ammonium hydroxide in this reaction, what I would do is I would scan across and down until I came up, I'm going to erase that because I wrote over it, until I came to the ammonium hydroxide part of the table. And what I see is AQ. Ammonium hydroxide is aqueous in water or soluble. This means that it would not form a precipitate. Let's look at another one though. What about Cobalt to oxide? COO. Is Cobalt 2 oxide soluble in water? So we're going to find the cobalt cation, Cobalt 2, and then we're going to find the, oxide anion, O-, and we're going to come across, we're going to come down, and when they intersect, we find out the solubility of that ionic compound in water. And here we see that it says I. I means insoluble in water, or not soluble in water. So this means that if you reacted a solution of 2 ionic compounds and it produced Cobalt 2 oxide, you would produce a precipitate. Now, why is that important? We're going to go back because I think the solubility table is easy to use. A formation of a precipitate is one of the evidences that a chemical change occurs. So if I tell you that a precipitate formed, like here's AB, if I mix this with solution CD, when I mix them, a precipitate formed. Did a chemical reaction take place? You would say yes, because when you form a precipitate, a chemical reaction occurs. Another way I could ask this, I could say, predict the possible products of the reaction, and then tell me if they would react. So if you would do the double displacement reaction, and I'll show you in a second how to do that, but if they formed a compound that was insoluble in water, a precipitate would form, and that's evidence of a chemical change. Okay, remember I told you need to know these evidences. Maybe I could ask you what 3 evidences of a chemical change were. You could tell me heat, precipitate, and the third is formation of a gas. Now, there are 3 times basically gases are going to be formed in double displacement reactions. The gas that's always going to be formed varies, right? But what they form from, there's 3 different reaction products that are going to produce a gas. If you ever form carbonic acid as a possible product, carbonic acid is H2CO3. That is not going to be stable. It's going to break apart or decompose further to form carbon dioxide and water. So if you take any reaction and one of your possible products is carbonic acid, H2CO3, that's called an intermediate. It's not stable, and it's going to further decompose to form carbon dioxide and water. Now, we know water is a liquid, and since we're doing aqueous chemistry, you're just putting more water into the solution, more of the solvent. The gas is going to be the carbon dioxide. We know carbon dioxide is a gas. So when carbonic acid's formed, it will replace or it will go ahead and further react to form liquid water and carbon dioxide, CO2. You'll see bubbles from that reaction. This is actually the famous, produced in the famous volcano reaction experiment. So if you take sodium bicarbonate or sodium carbonate and you react it with acid like vinegar or hydrochloric acid, you'll produce carbonic acid in those little volcanoes where they always bubble, in the high school experiments. You'll get carbon dioxide out as the bubbles and liquid water. Okay, what's the other time that you're going to produce a gas? There's 3 instances where you can produce a gas in your products. If you ever predict that one of your products is H2SO3, H2SO3 will also further break down to spit out water, but it will further break down to spit out sulfur dioxide. Sulfur dioxide is a gas, so this is metastable. It's an intermediate. It will further decompose to form sulfur dioxide and water. The third one is if you produce ammonium hydroxide. Ammonium is NH4 and hydroxide is OH. If this is formed as a possible product, it's not your product. It will further decompose to form water and ammonia, NH3. Now, I know I wrote all over that so you can't see it. That's because I want to show you what's going on here. We said there were 3 things that will further decompose to form a gas. So remember, keep straight what we're doing here. We're looking at the 3 instances that we can predict where their gas forms. So if one of the possible products you predict, we said was carbonic acid, then that would form a gas plus water. We said if you formed sulfurous acid, right, that would also be metastable. It would further decompose to form a gas plus water. And the same thing was true for ammonium hydroxide. It would react to form a gas plus water. So we haven't talked about how to predict the products completely yet. But if you predict this product, or this product, go, oh wait, these are the 3 products my professor told me to memorize, or the book talked about, because it's all in the book, that they're not going to be stable. They're going to further decompose and react to form a gas. And that's evidence of the chemical change. Now, what do you see in common with all three of these reactions I've just showed? All three of these decompositions. What do they all produce? Doesn't each one of them produce water? I say spit out water. What do I mean by that? Okay. We're going to take these chemical equations given, because the gases formed in each case are different gases, but you can predict what the gases are if you memorize these three and know that they decompose water out. Water is H2O. So in each case, from carbonic acid, for instance, if I remove 2 hydrogens and oxygen from this formula, so remove the 2 hydrogens, which is all of them, and 1 oxygen found in water, 3 minus 1 is 2. What's left? CO2. That's my gas. That would be where the bubbles are coming from. Okay, let's do the same thing. Sulfurous acid, H2SO3. You're just going to have to memorize that that's not stable. It's going to further decompose. To form water, they're all going to spit out water. So once again, H2, subtract an O. So 1 oxygen, 3 minus 1. It's going to spit out the water. Our gas will be what's left, SO2. Okay, so the gas is whatever is left over after water spit out. Okay, let's look at the last one. Ammonium hydroxide. Ammonium hydroxide you're just going to have to memorize. It's metastable. It's going to further decompose. We're going to lose H2O. So here's 1 H and 1 oxygen. But we need to remove the second hydrogen. So 4 minus 1 will be 3. Oops, there's a 3. So we have NH3 left. So the ammonia, that stinky gas when you clean and you're like, oh, I'm getting a headache because all this cleaning stuff, that's ammonia, right? So ammonia is a gas, and it would produce bubbles in your reaction mixture. So there's 3 ways that we can predict chemical change occurring. If a reaction, I'm going to erase all this now. Oh, it's in my way. All right, so if a reaction forms heat, if you're in the lab and you pour 2 solutions together and it starts getting hot, that's evidence of a chemical change. The second, if you pour 2 aqueous solutions, which are clear, usually not clear, they're usually clear, transparent, you can see through them. They might have color, but they're translucent. When you pour those aqueous solutions together, if it gets cloudy, or you start noticing some solid particles falling out of solution, well, you formed a precipitate and a chemical reaction just occurred. And the third was, if you take 2 clear, transparent, maybe colored, maybe not, solutions, and you pour them together, and immediately the reaction starts to bubble, well, that's evidence of a chemical change. You have produced a gas in one of these 3 gas-forming reactions. Okay, now let's look at the reactions a little further. How in the world am I supposed to predict these products? Let's look at an example here. Sodium carbonate plus HCl. If I told you you had sodium carbonate, NaCO3, Na2CO3, because carbonate's minus 2, and what did I say, HCl? Hydrochloric acid. And let's make both of these aqueous. Okay, and remember, the reason that acids are in their own category, even though they're molecules, is because when they're dissolved in water, they're ionic. So they form ions. So both of these are technically ions in a water solution. What I do first is I might give you these reagents and I say, hey, predict the products that could possibly form in this reaction. Well, the first thing I'm going to do is realize that these are ionic compounds. So sodium carbonate is an ionic compound. Remember, ionic compounds have charges. The metal has a charge and the non-metals have a charge. So they're dissociated in solution, cations and anions, but each cation and anion has a charge. So I need to figure out what that charge is. Sodium on the periodic table in group 1A. So hopefully you have a periodic table around, or maybe you've memorized sodium's plus 1 charge. So sodium has a plus 1 charge. What is the charge of carbonate? Carbonate is CO3 2 negative. And if you can't remember, reverse the crisscross. Okay. But negative 2 charge. Nick the camel, right? It's got 2 vowels, so negative 2 charge. Okay. I'm also, before I even predict the products, I'm figuring out the charges of my ions. Why am I doing this? Why am I not just predicting products and switching the cations around? Well, cations have charge, and the charge is not going to change. So first of all, I need to tell what the charges are so that when I predict my products, I can rebalance the formulas, because I have to write balanced formulas for ionic compounds. So we're going to do the same with HCl. Hydrogen is a cation. It's going to have a +1 charge, just like sodium, it's in group 1A. Chloride has a -1 charge. Okay, so let's predict our products here. Let's see. When they react, if I asked you what are the possible products, maybe not what's going to happen, but what could happen, okay? What we're going to say is, if this is a double replacement reaction, then the cations will switch anions. So I'm going to take my sodium and my hydrogen. I'm going to switch places. So now I'm going to rearrange the ions. So instead of sodium carbonate, I'm going to have hydrogen carbonate. Now hydrogen has a +1 charge. Carbonate has a -2 charge. So here's my products. Now do you see what I'm doing here? I've written the charges down. Okay, now hydrogen carbonate is not HCO3. That's the number one wrong answer I'll get. Hydrogen carbonate is an ionic compound that's neutral because the charges overall are balanced. Because I only have a +1 charge, I've got a -2. I need 2 +1s to balance the -2. Excuse me, I've been sick all week. All right, so I'm going to erase my charges. Remember, we don't like to write charges in our final compound? Yeah, that's always bad. Okay, now, that's one of my possible products. The other possible product is what's left over. So we've got hydrogen carbonate, so I'm going to have sodium chloride. Okay, sodium is +1, chloride is -1. So now we see the charges are equal and opposite. Do we need to write any subscripts? No. All right, now we go to our, now we're going to do something else. Now I'm going to say, wait a second. Carbonic acid, that's one of the 3 reagents my professor told me was not stable and it will further decompose. Is this really a product of the reaction? Is this really what I get out when the reaction occurs? And the answer is going to be no, by the way. Because carbonic acid will further decompose to form, what's it going to spit out? It always spits out water. So we can predict that one all the time. And what's left is carbon dioxide. If you subtract water from carbonic acid, you're going to get CO2. Now, carbon dioxide is what physical state? It's a gas. Did the reaction occur? If I put these two things together, right now, will this reaction actually occur? Will a reaction occur, or will I just form a mixture? Yes, a reaction will occur, because one of the products will form a gas. And a gas is an example of evidence that a chemical change will occur. So yes, a reaction will occur. Now, the next question is, I've written down that carbon dioxide is a gas. I've written down that water is a liquid, because it's a liquid. But what about sodium chloride? What is sodium chloride? Is it a solid, liquid, or gas? Well, we know it's a solid in its natural state. But these reactions are not done neat or as pure substances. They are in water, right? So if I form an ionic compound, I need to ask myself, is this thing soluble in water? You're going to go to your solubility table, okay? And I'll give you one of these. But you're going to find sodium. Here's sodium. And you're going to find chloride. Here's chloride. And you probably already know the answer, but I'm just showing you how to do this. So you've got sodium, you've got chloride. Where they meet on the grid, notice how it says aqueous? Yeah. Aqueous is what you're going to write here, because it's soluble in water. So the question is, does this reaction form a precipitate? Does a solid drop out of the liquid? Is it something insoluble? The answer is no. Although it does form something insoluble, but instead of precipitating, it bubbles out of the solution. So a reaction will still occur, will form carbon dioxide. The sodium chloride will be ions that are just floating around in solution as they were before. Okay? So that's an example of performing a reaction, a double displacement reaction. You'll always need to balance the reaction afterwards. So just be careful with that. But basically, that's how all the double displacement reactions are occurring. Now, will you always form a gas? The answer is no. Sometimes you'll form a precipitate, and sometimes no reaction will occur at all. But I'll always tell you if heat's formed. But usually I'll say, hey, predict the possible products of these reactions below, if they're double displacement reactions, and tell whether or not the reaction occurs with the information given. So maybe I'll tell you bubbles are produced. Maybe I'll tell you heat's formed, or one of precipitates is formed. And might ask you which compound forms the gas, or which compound forms the precipitate. So be able to use those skills, all right?